We are recording. So, in Wellington, starting on the 26th of the 5th, we have Ali, Andrew, Blake, Cody, Emily, Finn, Kalani, Stefan, and Thomas. So, you guys are all in Wellington on the 26th. And then on the 9th, we have Antonio, Connor, Daniel, Ethan, Fergus, Hoira, Jack, Jacob, Jordan, Levi, Rex, Ryan, Sasha, Timothy, Troy, Tyler, and Zane. So there are more people on the second one, just because the first one is going to be kind of getting everything all sorted, and there will be some people there who are not part of this night class. And then in Napier on the 26th is Casey, Kieran, Max, and Sean. So that's the. No, that doesn't look right. Hold on. 26th of the 5th. I will look at the timetable. I'm just checking. I think you guys are actually before us in Napier. Look at the Napier timetable. Oh, not yet. 26th of the 5th. Yep. But you guys are in Napier, Casey, Kieran, Max, and Sean. So you guys don't have to come all the way down here to Wellington. You guys can just stay up the coast.
Sweet.
And obviously it's only for a week, and the reason we've got the gap in between for Wellington is because of King's birthday. It's already only a 1 week, so we don't want you guys to lose a week or lose a day because of King's birthday. So yeah, if anyone joins later, they'll be able to watch the recording back and hear their name. Hopefully, I didn't miss anyone. I did accidentally put someone on the list twice. So all the info. So you guys will come to block course. We've gone over some of the activities you'll be doing in night class, but it's not anything too over the top. It's all well achievable in a week. And basically, all you guys need to bring are your hand tools. I would recommend bringing drawing set, so compass, ruler, protractor, couple pencils, just in case some colored pencils, just because you might have to draw three-phase stuff. So your red, your yellow, and your blue, and then your green for earth and black for neutral. It's always good to do color orientation, color coordination. But with all that stuff about block course, we will get into tonight. So. Come on. Cool. Can everyone see the PowerPoint? Is there anyone who can't see the PowerPoint? Cool. I figured as much. So I will. I'm going share screen. Cool. How about now? All good, Jordan. We're just getting started. We were just talking about block course before. So where did I have Jordan? Jordan, your block course, if you didn't get the emails on the 9th of the 6th. Cool. So do a bit of revision. So last week we talked about the legal hierarchy of electrical regulation in New Zealand. So you've got the Electricity Act of 1992. It's the highest authority. It sets out a legal framework for all electrical work. We had the ESRs, Electrical Safety Regulations, 2010, and these define safety requirements, including risk classification. And then you have 3000, also known as the wiring rules. It's a cited standard under the regulations that must be followed. And then we've got our electrical codes of practice, or the NZECPs. They're additional guidance, and they're sometimes mandatory if they're referenced in the ESRs. And then we must understand this hierarchy to know which document takes precedence in decision making. So if there's something in the Act that's contradicted by something in the wiring rules, we go with the Act and we ignore the wiring rules because the Act takes priority. Oh, I don't know if you guys can hear it, but it has started raining quite heavily here in Wellington. Cool. So electrical work is categorized into the 3 risk classifications. Your low risk, minor jobs, replacing a socket outlet, replacing like for like. Your general risk, so most routine work, and it requires testing and certification. You got high risk work, including hazardous areas, main switchboard upgrades, medical installations, and anything that must be inspected and certified. So knowing these classifications ensures electricians follow the right compliance and certification process for their work. Just on that, how many of you guys have been on a site where you've had some work inspected? And what was being inspected? All good, Jack. Welcome to the chat. New board? Yep. It's because Andy, you may not have been there, but that entire hospital needed to be inspected. Solar panel shed, that's cool. New main earths, new mains boards. Cool. So then we get into 3000. So it's the foundation for safe and compliant electrical work. So the standard is legally referenced in the ESRs, like we talked about. So understanding part 1 is the fundamental principles is key before learning. And then part 2 is the installation rules. So we need to understand part 1, the fundamental principles before learning the installation rules. Cool. So this standard is also essential for preparing for the EWRB regulations exam. Cool. So what is the hierarchy of electrical regulations in New Zealand and why is it important? We're just talking about it. Yep. That's why it's important. Yep. Cool. So you've got your Electricity Act 1992, which then dictates your electricity safety standards 2010, which the ASNZS 3000 is cited in the standards. And then that also includes your ECPs if they're cited. And then if they're not cited, below that you have the electrical codes of practice. So if an ECP is cited but it contradicts 3000, which one do you think takes precedent? So if you've got a ASNZS 3000, which is a cited standard, and your electrical codes of practice, so one of them is also cited, which one takes precedent? So which one do you follow if they're both cited but they contradict each other? Yeah, the cited version. So it's a bit of a it is and it isn't a judgment call, but realistically, what you need to do is if they're both cited in the regulations, you need to go and see if there's an addendum or a exception. So if there's an ECP cited but it's got exception, or it says that the ECP should be followed over 3,000. So should say in the regulations if there is a contradiction, what to do. And failing that, you check the Electricity Act, and then if you still can't find anything, you make a complaint to the EWRB or get a electrical inspector to sign it off, because at the end of the day, they're supposed to know the regulations and the act better than we do as standard Sparkies. Um, I will get there one day, hopefully soon. But the reason these are important is to understanding the hierarchy. Oh yeah, cool. So you've got the issue in the solar industry. Currently working on a 2012 version, which is cited, and there are 3 newer versions in play, but we cannot install to these. Yeah, yeah. So there's always newer versions that aren't cited. And then as far as the solar versus 3000, my view would be that because the solar is newer, 2012 versus 2007, I would say the solar ECP would take precedent. Is that ECP 477 or is it a standard ASNZS 4777? Standard, yeah. So if it's a cited standard 4777, 2012, that would take precedent over 3000. But yeah, the reason it's important to understand the hierarchy because it helps us to follow the right legal requirements when making compliance decisions. Because this is all about protecting ourselves legally and to make things electrically safe. Because something can be safe but not compliant to the regulations. And like we talked about with a half finished job, it can be compliant to the regulations but not safe. Cool. So, what are the 3 risk classifications for electrical work and how do they affect compliance? Yep. So, yeah. So you've got low risk minor work that does not need external inspection. And although not required, it's still good to do an ESC for the job. Cool. Your general risk, so routine work that requires testing, but not always an inspector. Um, unless, of course, it's someone doing work under the homeowner exemption that requires inspection. So for this, you would issue a COC and an ESC. And then for high risk, it requires third-party inspection and certification. So electricians must follow the correct process to ensure work is compliant. Cool. So why is ASNZS 3000 so important for electricians, and why does it relate to the EWB regulations exam? I do like that answer, Connor. So yeah, 3000 containing fundamentals and installation principles for the job. Yep. And yeah, the EWO needs to make sure Sparkies are clued up before they start connecting to grids. Yeah, 100%. Cool. So ASNZS 3000 sets out the technical requirements for safe installations. So technical meaning the actual physical wiring stuff. It is cited in the ESRs, meaning it must be followed by law. And understanding ASNZS 3000 now makes studying for the EWB regulation exam easier later on. So by us taking you through kind of the basics in year one, and then we'll step it up in year two, by the time you get to doing your regulation study in year three, the book won't be as daunting or scary to you. Cool. Cool. So introduction of ASNZS 3000 and the fundamental principles. So we're going to go through some of the kind of basic stuff today. So we're focusing on the most important document for uh, electricians to follow. So the standard is to ensure safe and compliant electrical installations. So we'll look at an introduction to 3000. So why is it important? So okay, how to navigate ASNZS 3000. So yeah, sorry. So it's a legal requirement cited in the electrical safety regulations, meaning you must comply with it. You've got no option. You need to comply with the standard. Safety and consistency. It establishes minimum safety requirements for all electrical work. And that's something I want to stress to you guys is this is just the minimum. So this is the minimum safety requirements, but that is no reason why it's not a target, it's a benchmark. And the whole point is to go above and beyond that. Um, so, yes, I can get away with running 1.5 on a 10 amp breaker for my hot water cylinder, but I may as well run 2.5 and put it on 16 amp breaker. Or, yep, right now 2.5 is good enough for the load, but what if in the future they decide to increase the load and replace the machine and not check the cable size? May as well put a 4 mil in. But that's up to you guys. Again, it all comes down to cost versus cost and practicality. Cool. So it covers all aspects from design and installation to testing and verification. So it's the foundation of most electrical work. So you need to refer to it constantly throughout your career to make sure you are complying. Cool. So how to navigate ASN 3000. So it's a large document. When you chuck it down on a table, it makes a nice big thud. So you need to know how to find what you need quickly. So it starts with a preface. So it explains part one, the fundamental principles, versus part two, the installation rules. So part one applies to all electrical work, while part two provides detailed technical rules. So part one it applies to all electrical work, whereas part two just provides the detailed technical rules. So you got a contents versus the index page. So the contents page provides a high level overview, whereas the index page is useful for finding specific topics quickly. You've got an explanation page or a forward. So it outlines why the standards exist and who it applies to. It's pretty dry reading. You got the definitions, section 1.4. So this defines key electrical terms used throughout the standard. Cool. So now we're going to have a little bit of a fun task. Cool. So here is the contents pages for ASN 3000. So what I want you guys to do is I want you to, yeah, you can just go Control F, yeah. But if you're actually looking at the book in your exam, because you can't take a PDF into the exam. Cool. So I'm going to read out some things and I want you to give me a reference. They do provide you with some PDFs, but they're locked and you can't use Control F. I tried when I was in there. So what you'll do when you do your regulations course is you will get a copy of 3000 and you'll put basically you'll tab it. You'll put post-it tabs on it so you can reference things quickly. So one of the tutor who's taking that course will go through that with you, and then you'll get given yeah, places to put all tabs. Cool. So I want you guys. So if I'm looking for information about earthing, where am I looking? Yep. I'm gonna open the book and I am going to go to section 5. Yep, cool. So what about underground wiring systems? Yeah, if I'm looking for underground wiring systems, I'm going to go to section 3 because it says selection and installation of wiring systems. Then I'm going to go down and section 3.11 is going to catch my eye, underground wiring systems. Cool. What about motors? Yep. I didn't know there was a section 34, Sean. I'm guessing you slipped on the keyboard. Yep. So I'm going to go to section 4 because it says selection and installation of appliances and accessories. Well, good, Sean. And then I'm going to look down and then I'm going to see motors in 4.13. Yep. Cool. So then I need to find out some information about visual inspection. Where am I going to go looking? Yep. So I know that visual inspection is part of the testing or verification section. And then I'm going to go to section 8 and I'm going to look down and see that visual inspection is 8.2. So what about socket outlets? Yeah. So yeah, I know that a socket outlet, as far as the wiring rules, is considered an accessory. So I'm going to look in section 4 and then see in 4.4, I have all the info I need about socket outlets. Cool. So what about fault protection? Yep. So I'm going to hear the word protection, and then I'm going to look at section 2 because it's general arrangement of control and protection. I'm going to look down, and then, yep, in 2.4, I see fault protection. Then what about baths and showers? How about that, guys? Just having a look at who's here. Yep. Cool. Yep. So I know that a shower is considered a damp area. So then I'm going to look down in the damp areas or damp situations in six. So yep, 6.2 is baths, showers, and other fixed water containers. Cool. So what about batteries? Yep. So I know that batteries are classed as an accessory. So I'm going to look down to my accessories in section 4 and see that batteries are 4.17. Yep. And then what about my equipotential bonding? I have a Rex question about equipotential bonding, or I need to know if something requires bonding. Yep. So I'm going to go back to my earthing arrangements. I'm going to look down on the list of contents, and yep, I can see 5.6 equipotential bonding. What about high voltage electrical installations? Yep. So as soon as I hear high voltage, I'm looking at the special electrical installations in section 7. I look down and I say, yep, 7.6 high voltage electrical installations. So yeah, once you understand where something fits into things, it's quite easy. Sometimes it's not always clear, but generally looking at the contents, you can be, yep, cool. I know it fits into this category. It should be under this heading. And then once you've done all your tabs in year 3, you can quickly, yep, it's this tab, pull it open, and you're away. Cool. So now we'll look at the 14 fundamental principles. So 14 fundamental principles of AS/NZS 3000 ensure that electrical installations are safe, reliable, and compliant with regulations. Each principle ensures electrical installations meet safety, design, and operational standards. As we go through each, so make sure you take notes on each of the points because we're going to apply them to scenario-based discussions later. Cool. So 1.5.1 protection against dangers and damage. So, electricity is dangerous. Our job as electricians is to make sure installations are safe. So, this principle ensures electrical systems do not create hazards such as electric shock, fire, or mechanical injury. Installations must be designed to prevent direct harm to people, property, and animals. The switchboard installed in a wet area must be waterproof to avoid faults. So each of the principles we're going to outline, they're a key requirement that all electrical systems must follow. Um, so as we go through, we'll talk about its purpose and look at a couple real world examples. So yeah, so pretty basic protection against dangers and damage. So we're just making sure that we protect against anything dangerous and damage. So a switchboard installed in a wet area must be waterproof to avoid electrical faults. But obviously there are in 3000 we have restricted areas where a switchboard cannot be installed because it would be too open to access from water damage. So this is the basic principle, which we then turn into a um, basically a rule in part 2. So part 1 is about what we need to ensure. Part 2 is how do we do this. Cool. So control and isolation. So we need to be able to safely switch power on and off. So all electrical systems must have a clear, accessible control point for operation, maintenance, and emergencies. So all electrical systems must have clear, accessible control points for operation, maintenance, and emergencies. So it includes isolation, emergency shutdown, and maintenance switching. Example, an emergency stop button on an industrial machine ensures power can be can quickly be cut off. So this is then turned into what requires isolation and how we can do it safely. It's things like minimum height requirements for main switches to make it accessible for everyone, and a minimum height that it cannot be below, otherwise it's hard to see. That's the reason why it should be above 1.2 meters, because if it's below a meter, it's harder to see it. And if it's above 1.8, it means that it's harder for people to grab at it. Although obviously you can get exceptions to these. So if you had a main switch in a property that is purpose built and designed for, so it would be done to a certified design, people who are, let's use the medical term, who have dwarfism, then obviously you would try and you would use part one and have it designed specifically so that they could operate their main switch safely. So you would override part two with part one because they need to be able to turn off the power safely and they need to be able to access their main isolation point inside the property. Cool. So protection against electric shock, 1.5.3. So electric shock can kill. We need to protect against it at all times. So electrical systems must prevent electric shocks under both normal and fault conditions. So there's two main types of protection. So 1.5.3.1 is basic protection, so direct contact protection, prevents accidental contact with live parts. And then you have 1.5.3.2, fault protection from indirect contact. Indirect contact ensures that exposed metal parts never become live. So direct contact, so is live parts, and indirect contact is ensuring that exposed metal parts never become live, which is how we get our bonding requirements, because we reduce the potential difference to zero by bonding it. Cool. So an example, an RCD or residual current device, it cuts power if someone accidentally touches a live wire or touches a surface that has become live because, oh, I was going to say, no, and then a circuit breaker would protect and bonding protector would protect against metal parts becoming live, because if they're bonded and the phase touches it, it'll cause a short circuit, which will trip the circuit breaker. Or it can even, if it's small enough and a high resistance enough, it may cause just enough leakage current to trip the RCD if it's an RCD protected circuit. Cool. And then you got 1.5.4, which is basic protection, protection against direct contact. So we must stop people touching live parts. So there's four methods to prevent direct contact. So you've got your insulation, wires must be covered with durable, non-conductive material. Barriers and enclosures, live components must be kept behind protective covers. Obstacles in restricted areas, obstacles prevent accidental contact. So protection against direct contact. So it's all about being stopping people from touching live parts. So that's putting barriers in place, insulating the cables, putting obstacles in the way so people can't accidentally get to them. You can place things out of reach. So high voltage conductors must be placed where people can't reach them. So if people can't get hold of them without using a ladder, or for the high voltage lines, I think you'd either need a crane or a cherry picker for some of them. So an example is your PowerPoints have plastic covers to prevent direct contact with live pins inside. So you can imagine if our PowerPoints were literally just three open metal holes that were big enough for you to stick your finger in, you would definitely not be protecting people against direct contact. The other one to look at is how a lot of modern PowerPoints have um, covers that mean that you cannot uh, insert um, a prong into the phase terminal without also inserting a pin at the same time into the neutral, which stops people from being able to stick metal objects into them. Cool. And then 1.5.5 talks about fault protection. So protection against indirect contact. So even if a fault occurs, it should never put people at risk. The British ones aren't that big, but they are chunky. So if fault occurs, it should never put people at risk. So 5 ways to protect against faults. So you've got your automatic disconnection of supply. Power cuts off immediately when fault is detected. That refers to your circuit protection. Your double or reinforced insulation, so extra layers of insulation to prevent faults. That's why we even conduit wire has it. So conduit wire has extra reinforced insulation, and TPS has double 2 layers of insulation. You've got your electrical separation, so your isolation transformers ensure faults don't spread. You've got your extra low voltage, safety extra low voltage, and protected extra low voltage, using low voltage for safety. So example, if a fault occurs inside a metal appliance, earthing ensures the metal doesn't become live, or if it does, it trips the circuit breaker. Cool. So 1.5.6 talks about additional protection by the use of RCDs. So RCDs provide a second line of defense against electric shock. There's 3 key points. So RCDs must be used in high-risk areas, such as bathrooms and outdoor installations. So they detect leakage current and disconnect power before a person gets a dangerous shock. They cannot replace basic protection, but enhance safety. So just because you have an RCD doesn't mean you can skip other types of basic protection. So example, power tool plugged into an RCD protected outlet cuts off instantly if the cable is damaged, but you still need short circuit protection and other forms of protection. Cool. 1.5.7, basic and fault protection by use of extra low voltage. So low voltage reduces risk, but it still requires proper installation. So using separated ELV or separated extra low voltage or ELV, protected extra low voltage, can provide both basic and fault protection. So extra low voltage systems under 50 volts AC or 120 volts DC reduce shock risks. For example, doorbell circuits often use 12-volt transformers to prevent electric shock hazards because you're literally, if you break the button as you're pushing it, you're basically bridging the 2 contacts with your finger as you push into it. Cool. Protection against thermal effects in normal service. 1.5.8. So electrical equipment generates heat. We must control it. So yeah, if you have a motor spinning under load and it's a little bit more than it can handle, but it can still spin it, you'll find the motor will heat up, especially if not adequately cooled. One of the things that one of our tutors did here in the workshop is that he took 2 of our 3-phase motors and he joined them together at the keyway, and basically using one motor to spin the other. So what we noticed is that as we ran the motor for long periods under load, we were actually overloading the motor a little bit and it was getting quite warm quite quickly. So we quickly turned it off. So it prevents overheating, burns, or fires caused by normal electrical operation. So an example, light fittings must be kept away from flammable materials like wooden ceilings. So yeah, if you have a wooden ceiling and you're using high temperature lights, you need to have some form of separation so that way you don't set the wood on fire or scorch the wood. So 1.5.9, protection against overcurrent. So too much current equals a serious problem. We must prevent it. So electrical circuits must be designed to handle safe current levels. Circuit breakers and fuses must be rated correctly to prevent overheating and fire. For example, a 15 amp fuse in a 10 amp circuit would be dangerous because it won't trip fast enough. And that's where we get the rules around discrimination and current ratings for our cables. So 1.5.10, protection against earth fault currents. So if an earth fault happens, power must disconnect instantly. So earth leakage protection ensures that current doesn't leak to exposed parts at a value that allows conductors or parts attaining excessive temperatures. So an example is RCDs detect leakage current and shut power off immediately if a fault occurs. Or if there's an earth fault and it's a short circuit to metal, the bonding conductor creates a low resistance path which will trip the circuit protection. Cool. So protection 1.5.11, protection against abnormal voltages. So surges, spikes, and drops. We need to protect electrical systems from all of them. So there's 5 subsections to cover. Protection against abnormal voltages caused by faults in live parts at different voltages, induced into otherwise unused conductors, or occurring as a result of issues in other circuits or installations. So one thing to remember about when you bunch cables together, if one of them is disconnected at the switchboard and at the power point end, if other cables that are bunched together are drawing enough current, they will induce a current and voltage into the other conductor. So one of the tests we do here at the workshop is we have 2 circuits mounted in 2 mounting blocks, one on top of the other. One is fed by red phase, one is fed by blue phase. So the students or trainees will disconnect the one for the top power point, but because there is still a voltage present in the other cable, you will still get 4.2 volts in the circuit when it's disconnected because the power point below it is live. 2, protection against electromagnetic influences. So 3, segregation of circuits to prevent interference. So splitting up your data and your power to stop signal degradation. So an example is surge protectors prevent lightning strikes from damaging home electrical systems. So 1.5.12, protection against the spread of fire. So electrical faults should never start a fire. So wiring and components must be installed to minimize fire risk. Example, fire-resistant cables are used in emergency exits to ensure lights remain on in a fire. It's one example. One other example is that if you have a gap in your switchboard or an opening in your switchboard that is greater than 5 millimeters, it needs to be fire sealed. All openings in your switchboard should be tight fitting or subsequently sealed to prevent the spread of fire. Cool. So 1.5.13, protection against injury from mechanical movement. So machines and moving parts can be dangerous. Electrical systems must be designed to prevent accidental activation of moving machinery. Example, emergency stop buttons on conveyor belts immediately cut power to prevent injury. And we must ensure that all of our emergency stop buttons completely stop the machine and we cannot reactivate it without deactivating that emergency stop button. And then we have protection against external influences. So weather, chemicals, and physical damage, we must consider all risks. So electrical systems must withstand environmental factors such as water and moisture, heat and cold, corrosion and chemical exposure, physical impact. So example, outdoor power points must be IP rated for waterproofing. In industrial settings where there may be corrosion, heat, and chemical exposure, we should use steel conduit instead of plastic because plastic conduit can be affected by heat and chemicals. And that's the end of PowerPoint. Oh, where am I? Okay. Now we'll do the activity. Cool. So I will read each electrical issue carefully, and then I want you guys to tell me which fundamental principle applies, and then why this principle is relevant to the situation. Cool. So, situation one, metal conduit becomes live after a fault. An electrician is called to investigate a fault in a commercial kitchen. A damaged cable inside a metal conduit has caused the metal to become live, giving staff mild electric shocks when touching nearby equipment. Which fundamental principle applies and why? So we're to look at this. So I can see why most of you would think 1.5.3 would apply. And yeah, but the so the one that most applies is 1.5.5. So fault protection against indirect contact because they're getting shocks off of nearby equipment. Um, so the system failed to automatically disconnect the supply when the fault occurred, exposing workers to electric shock risks. Proper earthing and RCD protection should have prevented this. Cool. So I will put the next one in the chat just in case. Cool. So a breaker fails to trip, overheating cables. So a workshop experienced an electrical fire in a distribution board. Investigation reveals that a circuit breaker failed to trip after an overload, allowing cables to overheat and ignite insulation. Which fundamental principle applies and why? All good, Fergus. Just if you want to watch the rest of it, it'll be on the YouTube channel later. Yep. So most of you guys got it. So it is. So point eight more refers to thermal effects such as insulation. 12 is more about spread of fire. So I can see where you would go with that. But the answer to this one is 1.5.9. Um, so protection against overcurrent. So the installation must include correctly rated fuses or circuit breakers to trip during overloads, preventing excess heat buildup that could lead to fire. So the circuit breaker failed to trip in an overload. It experiences a fire in the distribution board, but it didn't say anything about the actual distribution board spreading fire. So if you were to get that question in an exam or anything, it would be 0.5, 0.9 because it's protection against overcurrent. Cool. So here's the next one. So solar inverter producing high voltages during a fault. So a residential solar power system experiences a fault, but the inverter continues producing power at high voltages, creating a safety hazard. The system does not automatically shut down as expected. Which fundamental principle applies and why? So we've got 5 questions in total, so we're just over the halfway mark with this one. Okay, so point five is more about contact, so that's not really applicable. And then 0.14 is against external influences, which you could argue the solar power itself is an external influence. Um, yeah, so it's point 1.5.11 protection against abnormal voltages. So electrical systems must prevent voltage fluctuations that could damage equipment or endanger people. Inverters should have automatic disconnection features when faults like this occur. Is your answer. Cool. So installing a light fitting in an industrial freezer. An electrician is asked to install lighting inside a large walk-in freezer that operates at sub-zero temperatures. The client suggests using standard indoor rated light fittings. Which fundamental principle applies and why? So I was going with point eight. So point eight more refers to the heat thermal effects in normal service. So it's more talking about the machine generating heat itself. Whereas a lot of you guys, yeah, so 1.5.14 protection against external influences. So things like water, moisture, heat, and very effing cold. So electrical instrument must be suitable for its environment. Standard fittings might crack or fail in extreme cold. So temperature rated moisture resistant fixtures must be used. Cool. So no isolation switch for a large machine. So factory installs, yeah, more like oven or a motor in normal service. So providing adequate cooling so that the electrical equipment itself doesn't create too much heat, or making sure that the cable is um, not going to be overrated and catch fire. Cool. So yeah, no isolating switch for a large machine. Factory installs a new conveyor system, but the electricians forget to install a local isolation switch. This means workers must walk to the main switchboard across the factory, turn off power during maintenance. Which fundamental principle applies and why? Yeah, so yeah, it is 1.5.2 control and isolation. So machines must have local isolation points to ensure they can be safely turned off for servicing without relying on distant switchboards. You need to be able to switch off the power locally. Cool. So that is a wrap for tonight. I encourage you guys to, if you have access to 3000, um, get a hold of the principles and read through them and start familiarizing yourself with the different sections. Because next week, I believe we're going to start looking a bit closer at things like that. Yeah, next week we'll be taking a look at part two and the installation rules. So some key points to take away. So 3000, the wiring rules is the primary standard we use. So we have part one, the fundamental principles, which we've talked about tonight. The reason, so basically what we have to achieve, and then part two is the specific rules and how we set out to do that. So the 14 fundamental principles ensure installations are safe, functional, and compliant, and we must apply these principles to all installations before moving on to specific rules in part two. So just because in part two it looks like it will comply, if we look at these first 14 principles, it may not look as safe as it did when we looked at part two. Yeah, make sure you do all your assessment work on the Hive, guys. Don't leave it too late and let it lock, because you guys will need to use that email that we talked about. I am going to.